Okay, so the idea of today's discussion is to talk a little bit about gamma reverse emission mechanisms, and maybe if we have time, even something more about energy dissipation mechanism, which is particle acceleration mechanisms. Of course, it depends how far do we go. And I will start from discussing problems in gamma reverse spectrum. The problems I will start discussing the observations, and then I will make some claims and proposals to you, sort of, and then we can. And then I will introduce the model, which is nowadays I think becoming more and more standard model, which is written here. Electrons are cooling fast, but the heating is slow, and we will discuss all this. And so, some of the pictures that or simulations that you will see are done by the Boris Stern in the group. Okay, so the plan is that I will talk a little bit about gamma reverse spectral properties. Of course, you all already heard many talks about this. I will do it very briefly. I will talk about Sinterfeld and Compton, what people normally talk about as the main emission mechanism of gamma reverse. And we will discuss a little bit whether the electrons are cooling or not. And of course, we will see that they are cooling rapidly. Then for that, we will introduce a third model, which is called slow heating or acceleration model. And these are 5 points that I would like to go through, some very simple physical arguments, some numerical codes that one can use to study those, and important radiation processes, and I will summarize later. So we will start from gamma reverse spectral properties. As you all know, typically gamma reverse spectra are fitted with one component, which is called GRB function or band function, which is described by two power laws with photon indexes alpha beta somehow connected. And the result from analysis by Rob Priest from 2000 is that we are interested in, for example, with index alpha, low energy index, that there is a peak at about -1, which tells you that every time typical gamma reverse has spectrum typical, sort of like Ramshackle spectrum, that nu goes like nu to power 0, but there is a long tail which goes until up to nu to power 1. And even there are some few bursts that clearly show even harder spectrum that Felix was talking during his talk about, and that's also mentioned. Okay, so this actually results about hardness of spectra of gamma reverse was known for more than 20 years. I found one of the oldest papers on that. I'm sure they're even older. I found a paper by Moore and Epstein from '87 where they write that the steeply rising X-ray spectra, it should be array, there are someone missing here, can be regarded as one of the securely determined aspects of gamma reverse, since it has been independently measured by several research groups and there are no reported counterexamples. So this was already claimed more than 20 years ago, and this is completely, fully supported by the Betsy data, as I showed you from 2000 paper. It is still supported by the GBM data, I think. And so there are hard spectra in gamma reverse. Sometimes they are soft, but very often they are hard. Okay, what is hard for us? Okay, just briefly some other properties that we might start discussing later. Gamma reverse shows spectral evolution, as already I think Felix and Brasov showed, that this is the peak energy, how it goes during the burst. So it starts from 600 to 800 TeV with and then drops to a few hundred. So basically, the gamma reverse, when you have a nice pulses as shown here, and you can do time resolved spectroscopy, you see how the pulse shifts from high energies to low energies, how the peak of the gamma reverse shifts. Okay, as was already discussed before, sometimes you see components which are sticking up like that, which you might interpret as a thermal emission. Might be, why not? And of course, if you have such a component there, they might explain you the hardness of the spectrum. And if you would have those thermal components and you would like to look at the underlying power law, then this is what was distribution, sort of the same kind of distribution that Rob Priest was showing, but a different, a little bit format. And this is the distribution of these power laws that are left after you subtract the thermal component. As of course, it's clear that these spectra are softer, but still there are some components that are below cooling slope, which is 1.5 here, and I will discuss, of course, this cooling problem here. So, but at least if one believes in those thermal components, this problem that we will discuss later is not so extreme. is just only a few bursts are, maybe 20% of bursts are harder than photon index 1.5, while here in this diagram, as you will see, many spectra are harder than that. Okay, another property of gamma bursts is, of course, sometimes, we don't know whether it happens often, we don't know good instruments, there are other components. Here in 1964, 10, 17 gamma bursts, it seems that there is 100 eV emission that has sort of light curve smoother than the gamma bursts in MeV range, and it also twice as long. Okay, there is also sometimes prompt emission. In, for example, 9903 or 1923, that is like here, I don't know, 4 is magnitude larger than the continuation of the power law from MeV range, so it clearly requires some additional physics. There is another recent naked eye burst where you also clearly see the optical emission, and this is the light curve that you see lower in the conference. This is the continuation of the band function, and these are the alterations in optical emission. So it's also like 4 is the magnitude above the continuation. So there are only a couple of examples of this bright optical emission. Most of the time optical is rather weak. This is my plot, so if you wonder where you've seen it, you haven't seen it before. This picture, but just taking the data, putting it on the plot. Okay, so just to summarize the spectral properties, this is supposed to be proportional. Here, so we have a rather broad distribution of spectral indices. If you just feed it with the power law, with the band function, typical photon index -1, but there are spectra going up to alpha 0, which means that this goes like f mu goes like nu to power 1. There is status soft spectral evolution. Sometimes, always maybe, there is strong or weak, or some thermal component, maybe. Sometimes there is a 100 eV GV component. Some gamma Fermi bursts show sort of not so strong signal there, so some people start to wonder if there is another component, but maybe we will see later examples that there will be. Fermi will find such examples. And as Giancarlo, who has left, I think, just playing with the GCN circulars, he showed that in 10th of May 2009, the 3 week ago burst, there is a second component, just playing with the numbers that you get from GCN circular. Okay, if you fit it with power law, getting the same number of counts, you clearly get the second component, which is very bright. So maybe it's similar burst to what we have from GRB 1904, 10, 17. And sometimes you have prompt optical.
That's a short GRB.
That's a short GRB, exactly. Yeah, so which is nice also. This was a long GRB. This was 200 or 100 seconds long, and this was less than a second long. And sometimes you have prompt emission, which is also very bright, much brighter than you would expect from emission of the power law. The important thing which I haven't mentioned probably, that this hard emission and the soft, the optical emission, they seem to be delayed relative to the gamma reverse, to the MEV emission. And it's clear they're not sort of coming in phase. And this is all probably tells you something. Either this is a completely separate component, or this is related to the afterglow, we can discuss this, or this is related to the same outflow which just dissipates at some later time with optical thin regime when you can produce GV emission and they can escape, and optical emission can be produced by synchrotron, whatever. But these are the data. Okay, that was part 1. I think I did a rather good job. 10 minutes, all the spectral properties gamma reversed.
Just wait, you're still not interrupted.
Yeah. Because I haven't said anything yet new.
Not only quick, but very clear. So,
okay, so then we go to synchrotron or Compton Coulomb knot. Of course, often what people do, they inject or they assume that we have MEV emissions produced by synchrotron. So how it's done, you have the magic, you have a shock, particles are just thrown up there, and they have some power in the spectrum with some gamma min, gamma max, and then people just compute synchrotron emission from these electrons, completely neglect what happens to those electrons afterwards, most of the time. Compute some Compton, sometimes, maybe even not compute this. In reality, what happens, it doesn't matter what you do. If you inject electrons in the region with reasonable parameters for gamma reverse, electrons will cool. And the cooling time scale is much, much, much smaller than typical dynamical time scale of the system. I don't know what happened here, but this is supposed to be gamma. So the cooling time scale in the system, one can estimate as the light crossing time, whatever block you are looking at, divided by the compactness, divided by the gamma, which is the Lorentz factor of the electron. This is supposed to be gamma. And for typical parameters of gamma reburst, of course, compactness is of the order of unity, it can be larger than unity, and gamma is, if you want to have it by synchrotron, it will be actually much larger than unity. So this, of course, is much larger than unity together, therefore, this is the proof. The electron cooling time becomes much smaller than light crossing time. Just here, the estimation of the compactness parameter, it's like the energy, isotropic energy, 10 to 52 ergs, Lorentz factor in hundreds here, and distance in, from the black hole, from the central source is 10 to 15 centimeters, and it's about 10 here. So if you want to have, and here assume that the jet has opening angle 1 over gamma. So here actually the Permuven size is this size divided by gamma. Okay, this is of the order of unity. You can play with those parameters. You cannot really get terribly much different. But the important thing is that gamma is large. Okay, so of course the obvious result from this cooling is that the spectrum that you get is so-called cooling spectrum. So synchrotron, low energy synchrotron, if we just look at the low energy synchrotron, low energy electrons that produce synchrotron in MEV band, if we assume that they are producing synchrotron in MEV band, they produce the spectrum which looks like that. Here the photon index is -2/3 or energy index +1/3 as optically thin synchrotron. But because the electrons are cooling in time like that, you get photon index -3/2. You can play a little bit, as for example, Frederick was saying that if you put Compton scattering there, because of Kleinian effect, you can get it slightly harder. Not terribly much, but I mean, because Compton has to be accounted for, you can get this thing harder. You can also play that this region, the magnetic field is changing when the shock is propagated. You can also get this a little bit harder, maybe, but you can get really very hard.
Why do you call this Giussellini oscillator antenna? This was long before.
They just said many wrote special papers discussing those problems for gamma reversed.
What did you say?
They just wrote specifically discussing these problems for gamma reversed.
But other people wrote.
Okay, so if you show me
specifically about this problem before them, including this problem, it was relevant to the spectrum of gamma reversed.
yes, I mean there was a paper from '84 by Bussard that I found who was mentioning this problem. Even Murray Epstein was from '87.
From '84, you did not have BATSI spectrum.
But you don't need that. As I said, these results were known from '70s that the gamma reverse spectra contradict the Coulomb spectra. The result was known 30 years ago, and people still ignore that. So this is our distribution from Price et al. I mean, in the paper by Price, he called this synchrotron death line. So basically, all these spectra contradict optically thin instantaneous spectrum of synchrotron spectrum. In reality, the death line is here, cooling death line, and so 80% of the bursts, or 85, contradict this. 90%. You can count how many bursts left here after I probe. So these are allowed bursts by this model. Other are not allowed. So, first proposal. Should we stop writing and accepting as a reference papers, ignoring those simple facts? Because if you look at the literature, there are still papers just claiming that synchrotron is producing gamma reburst, MEV emission, and the electrons are injected in shocks. Okay? And since they are cooling, you should get cooling spectrum. This is strongly contradicts the data. So this cannot be the case.
So you know the data? No.
What?
You know the data?
No, the data are known for 30 years. There are no single instrument that is disproven. Okay, so
I made this point out earlier, but this is based on this underlying assumption that it's easy to forget that you separate the injection and the cooling. The injection involves particle acceleration. Particle acceleration can take place while cooling is still going on.
perfect.
So you cannot separate all the acceleration possibilities from the cooling possibilities, and you can have second-order acceleration
Perfect.
to accumulate electrons into.
This
a
is what we will
density.
discuss now.
Oh, okay.
Check. Perfect. This is exactly what I want to hear.
But that still doesn't.
No,
The
what
second-
is
it doesn't beat
contradictory?
the second line of death. It beats the first line of death.
Yes, exactly. This means the first. If this is what we discussed in the slow cooling,
All
so
right.
or slow acceleration, because the problem is that many papers just say that we inject electrons.
Well,
After that, they cool.
Sorry, I didn't mean to interrupt.
Okay, fast
I'll be
acceleration.
just straight man.
Because the typical shock first for the Fermi acceleration is very fast. So just particle accelerated, then they go downstream, they're lost. They're just gone. And they cool down. So they gain energy fast and they cool down.
I mean, there are other solutions, right, in the literature. There are at least two solutions that I worked on personally, so I know them.
No,
There
there's-
are plenty others. For
Okay.
example, one solution that we worked on a few years ago was the idea that the magnetic field does not persist over a very long
This is what I
time
mentioned.
scale.
Yeah.
So, okay.
And the second is the role of Compton scale, reverse mode.
Yeah, another is
Another.
scattering.
Another is jitter radiation.
So,
Jet radiation doesn't work, that's for sure.
We had a solution where
What?
Marcus Birch and I had a solution where you would have hot clouds upstream that get heated, and then you're passing your gamma ray burst radiation through this hot cloud and part.
We can involve another. So this problem, I mean, if you have change in magnetic field, that's possibly a solution. I'm not sure that you can get to very hot spectra.
yeah.
You can play as yesterday or 2 days ago, Frederick and Zelika showed that if you include Compton cooling, also you can get hotter spectrum, and so there will be some correction, but you cannot get those hot spectra. So I think there is a problem, and I think we should just be all aware of this problem. And I mean, maybe there is a solution, a simple solution which people haven't found out, but at least just still, it's particle injected, they cool. This doesn't fit the data. Okay, so what we can do to get the hot spectrum that we see in gamma ray burst. So one, the solution that Asaf was talking about, that if you think that there is a photospheric emission, then in reality underlying power law is actually soft, or much softer than we think. Okay, therefore, maybe it will be even consistent, or as I showed distribution, maybe 90% of the burst will be consistent with the cooling spectrum. Maybe those electrons are cooling just there, and they're accelerated in shocks. Then, of course, we will need to figure out whether this photospheric emission and the rest of the gamma ray burst, all those energetics are fine. What?
And if they interact, I mean, when
Yeah, because the photons interact with each other. So you have photosphere, right? And you have
physically
some
they
power.
coexist, I mean, if you inject particles further out, you have to take into account that you already have
Yeah.
a path of photons that could.
Yes, I mean this is what Asaf was doing in simulation, that you put power law, you put black body photons, then you have energy dissipation, you will have even synchrotron, additional synchrotron, because if you do it in the optically thin regime, you can have high energy radiation. That's fine. But I mean, this is the proper way of doing this. Then, if you think that this is photospheric emission, then okay, that's might be a solution. Another solution that also Jack mentioned, the electrons could be heated, or so they are slowly accelerated, or like second order Fermi mechanism, as I wrote here, yes, stochastic, slow heating, or maybe some magnetic dissipation scenario where you just heat the electrons on the time scale, which are much larger than the cooling time scale. And this, of course, allows you to keep the electron for many cooling time scale with the fixed electron energy, with the fixed energy. So you just, all the electrons will be piling up at some place and will be just kept there. Of course, then we have to remember that we have finite reservoir of energy. So if you want to give this energy to the electrons many times, not allowing them to cool, then of course one should keep in mind that you should conserve the energy at the same time. So you cannot give the same amount of energy all the time. So
I didn't get your argument. First of all, why time scale should be larger? The injection time should be shorter than the collision.
it's not injection. You should have heating. You should keep them
Oh, I mean the activity.
activity. So the electrons, so you don't want the electrons to cool down. So they have to have fixed electron energy. They have to have fixed energy, or more or less
You
fixed.
say you keep injecting. What's the problem?
You cannot inject them because you inject, they cool. They produce cooling spectrum.
What do you mean? You're assuming, you're already assuming the scales. You're assuming that injection occurs on a scale which is much smaller than anything else. Why
Yes,
should it?
no, that's fine. I mean, that is the way of then looking at this. So you cannot assume that the shock has injected electrons, and then you look how they radiate. So you have to think, okay, there are some processes that kick my electrons, and they heat it all the time, and that's the way.
Is there any known process that can do that?
Yeah.
I mean, there are some turbulence, sort of when the electrons just getting kicked by whatever magnetic turbulence, I guess. So they should be, which is called stochastic second order Fermi acceleration mechanism. Yeah. It could be anything.
The picture which you're envisioning are so naive. Just look at the AGN jet, you know.
Of course, this is naive. This is the simplest model. Then,
Dissipation occurs all over the place.
yeah, I mean, this is naive. This is mathematical model of, and whatever physics we want to put in, you're welcome.
Yeah, but I mean, these things are, that shows that the geometry community does not communicate with the
Exactly.
with other, because John Kirk and Mastiadish and all these guys worked this problem 25 years ago. I mean, they have all the calculations.
I mean,
you just plug in the GRB now.
I
and you get
mean,
them.
these things, all the slow heating. This is in the AGN community, in galactic black hole community for the last 40 years, I guess. Because when you talk about galactic black holes, you say, I have electrons which are thermal. Okay, why are they thermal? Because you heat them. That's the explanation. You don't know how you heat them, but this is the explanation. They're 100 keV all the time, in like Seyfert galaxies and Cygnus X1. This kind of, you heat them. Just you give them energy all the time, small amount, and they cool and they heat.
Well, Anatoly Spitkovsky showed a movie where particles are slowly heated downstream the shock, for example. You have different filaments and so on, and
That example.
short scale magnetic.
That was quite fast, I guess, because he was. It's very.
Yeah, the fast is
simple
when cross the shock, but when it's still downstream. And
But there's still very small scale what they're talking about. on
Yes,
short
but
simulation.
Anatoly box is on kinetic scales. you
It's
know.
very small,
The
yes.
dissipation itself, you know, you have obliqueness effect. You have some ejecta colliding with the world. I mean, everyone assume a conical jet, spherical shells accelerating, you know, in a conical way. This is unrealistic, in my opinion. If you look at just every time you have a good high resolution observation of something, that's not what you see. You see dissipation occurs all over the place. I mean, there are oblique shocks, there are. So I mean, well, I don't really
Yeah, I
see
mean,
what's the fuss about. I mean,
I
the
understand
problem
that there
arises
could
when
be
you're
shocks.
assuming a very naive picture. So then there is a problem. I agree. So that life is more complicated.
Yeah, very, very happy. So we can discuss mathematical construction of this model, slow heating acceleration model, right? Just so first, I think I will just do some very naive, also again, as Samir said, estimations. What do we expect? So basically, what we have a bunch of electrons which are described by optical depth tau, and I just give the luminosity L to them. Okay, this doesn't have proper units, maybe, or actually it does. Okay, but and so basically what I do, I just redistribute my luminosity on over some particles, which are given. Of course, this optical depth is somehow proportional to the density and so on. And on the right hand side, it's written the cooling. Okay? So those electrons, actually, they will be. This is just on the right hand side. You see that this is just the cooling rate, gamma dot. If you multiply by volume, so on, then you will get such thing which is proportional to the cooling rate of individual electrons. Where UB is the magnetic field energy density, URAD is the radiation energy density, gamma is the Lorentz factor. Okay, basically from here, okay, so this is heat and equal to cooling balance, because you want to heat them, you don't want the electrons to cool extremely fast. So when they cool, they produce synchrotron Compton. Actually, they can produce pairs, so they produce radiation, yeah. Those can produce electron-positron pairs, which you can compute, right? And so
I have a
this.
comment here that you miss a line from radiation to heating and acceleration because there can be a feedback because of the radiation you produce to
Here I assume that we
saturate
have a
acceleration
separate,
or
yeah.
whatever. So there is another line going
Yeah.
from the
If
bottom
you-
to.
We can put here the dotted line.
Okay. Okay.
In some models, you can imagine this situation. Yes.
Yeah, I mean you can.
This is the simple model.
Okay.
You can complicate this. So we don't know what here. This is the black box. Even it's yellow here, but it's a black box. Okay, as we will show the Compton Y parameter, in those conditions we will build Dodo of unity, which is a product of gamma squared times tau. Simple energy balance equation.
Wow.
Not very useful. Okay. I don't know. It was fine here.
Positive.
Ah, this. Okay. I think I should just write this on the blackboard.
All those equations? No!
No, I'm not going to write all the equations. I will just write 10 of them here. No, I think I will skip. Okay, I think you should just. I don't know what's happening here.
We believe you.
No, but this is really strange because it's perfectly.
It's changing in real time.
That's an exercise for the morning to get the right number.
But how it's possible? It was perfectly alright just 5 minutes ago.
Because Ben Q does not like Mac.
What?
Ben Q does not like Mac.
Oh, yours is mine.
Macintosh.
Very,
No, it's
strange.
not.
Very weird. You see?
I think that your computer disagrees with your model.
Yeah, very funny. Okay. I think it will be fine now. We just, if not, I will just throw it through the window.
It's probably enough.
Oh, it's a phone problem.
Yeah, but I mean, it's on my computer, so it's not something that I copied from somewhere. And it was perfectly right just 10 minutes ago. Before the talk.
Can you convert to PDF file?
No, but even now, even on my screen, it's the problem. Okay.
It's small phone.
No, it's okay.
It's okay.
No, no.
That's a
Did
small
you see?
phone. So that's,
Okay, it doesn't matter.
that's what it
We can skip. You just, you skip all the formulas. Very nice. So,
Spend 2 hours making.
what?
Spend 2 hours making.
They were done before all of this, so it's not so big problem. So basically, one can prove a simple thing. If you want to have your Compton y parameter, which is defined like that, Thomson optical depth times gamma square, you can write an equation which looks something like that: y times y. I will explain where you. And here you put the compactness of the energy what you put in. So this is basically luminosity divided by the size. And here you put the magnetic, which is called lambda beta. Basically magnetic compactness. So how much energy you have in the magnetic field. Okay. So this we don't know what's this ratio. Where this comes from is because you have cooling by synchrotron. So there is some UB is proposed. You have you have also cooling by so electrons are cooling by synchrotron. There is also Compton involved. So basically, just if you include 1 or 2 scatter nodes of Compton, which can be cooling your electrons, here it actually is 1, you get such an equation. So if y is of the order of unity, or actually larger than unity, then you get that y is of approximately L over lambda b into power 1/3. Okay, you just forget about those terms. So basically this tells you that y is of the order of unity if this is larger than unity. Of course, if it's much smaller than unity, then you should forget about those terms. And then you get y is lower than unity. But y cannot be much larger than unity because there is power here. And then, of course, this power 1 over something will increase depending on how many Compton scattering orders are still in Thomson regime, so you can Comptonize. So basically, depending on where you cut this off, it's still input with this. It's close to 1. You cannot get terribly hot spectrum.
But
This tells you.
doesn't this assume Thomson scattering?
Yeah, this is what I'm saying. That you cut this series where you have the final scattering order still in the Thomson regime, basically. And therefore, if you cut it on the next term, you will get just 1/4 here. So therefore, the more scattering order you have, the smaller power there will be. So it will be sort of smaller y.
Wouldn't you reach the Clinician regime after only the second scatter?
It depends on your parameters. Where is the magnetic field? Where is your Lorentz factor, and so on. This is just sort of more or less general form. What?
How do you define this lambda b?
Lambda b is dimensionless thing, which is something like that. So you have magnetic fields proportional to the magnetic field. And from here you just make the dimensionless quantity, which is, I think you multiply by sigma, mc square. What else do we need to divide by?
Radius.
Times.
What?
You need a
Multiply
radius.
by R.
Multiply by r.
No.
That's it.
Hendrik knows that. Okay, so he said that. That's it. Okay. So this is the typical definition. So, and for the compactness L, this is just luminosity over size sigma t MEC cubed. Okay, so it's similar thing. Okay, so interestingly, one can get the Lorentz factor of the electrons for those conditions. And the Lorentz factor of the electron, of course, you can get from here. Lorentz factor is just square root of y over tau. And so y we know, we just substitute there and we got the answer. So the Lorentz factor of the electron, which is close to unity because this goes like power 1/6, and you have optical depth into power minus 1/2. So this tells you that the result strongly depends on the optical depth of your electrons. This is the most important parameter here. And so small optical depth, let's put 10 to minus 8, just an example, you will get Lorentz factor 10 to 4. You will radiate somewhere synchrotron high energy. Optical depth unity, you get Lorentz factor of the other unity. So you have thermal condensation. That's what we have. So these are two extreme regimes.
Here you have all electrons.
Yeah.
What?
All energy electrons.
All the energy electrons. What do you mean by that?
I mean,
This is typical, yeah. Because the interesting thing here, if you heat gas, electrons will pile up. They will, it depends on what is your heating mechanism, stochastic or psychoanalytic Fermi acceleration. So they will pile up. In reality, you will get very close to Maxwellian. Because of course you always have thermalization mechanism. You can have synchrotron self-absorption, you can have Coulomb collisions at very high densities if you have enough. So you will always get Maxwellian, and then there will be this, some sort of, what do you call it? Deviations from Maxwellian. For example, if you produce pairs will be injected at low energies might be. So you will get some, I will show you some distributions which we can compute.
It's in assumption of no advection.
Yeah, here it's because
the
the
key point in this result.
advection where? Adiabatic expansion also we ignored here.
Yeah.
Just because the cooling is fast, you neglect those things. You don't need to care. So just an example. Okay, what you get? Typical Lorentz factor. Or if you have optical depth like 10 to minus 2, 10 to minus 4, then Lorentz factor is between 10 and 100. This is okay. Then, of course, if you do this, you can also do time-dependent simulations of this process. You just assume that you have a block, let's say. This formulas you have troubles today, but we will explain it in the hand. You have a block and you put this energy there over some time, or let's say over light crossing time, and you just compute what will come out. So we have done the simulations by two different codes, large particle Monte Carlo code by Boris, and then kinetic questions solving, which we have a paper just recently published in APJ with Interpro. Of course, on the market there are other codes. Assad wrote recently also a code which includes the same processes, almost the same process, not everything, but also the same. I mean, for these models, it's important to include cycle synchrotron radiation. Maybe even better if you have exact synchrotron radiation for low harmonics. If you have really optically thing like non-relativistic electrons, basically that then happens in this model. We need quantum scattering, pair production, pair annihilation, and here we also include all this thermalization mechanisms by Coulomb scattering and synchrotron self-absorption. Basically, in this kinetic question code that yes.
You don't have non-thermal, right? Non-thermal
No.
process.
What are non-thermal processes?
No, you have injection mechanism that with the time scale shorter than the cooling time.
Yeah, this is what we just ignored. We said that it's impossible.
Okay.
Because if you have injection mechanism, they cool. You get cooling spectrum. We cannot have it.
No, you're in principle, it's possible. Just you inject some number
At
of
high
atoms, and
energies.
then at high energies,
At high energies you can do it.
Produce
At high energies you can do it still.
yeah, they produce low cooling spectrum, and they
And then they
repeat
stop.
them, yeah,
And then they stop
and
somewhere.
then they stop and
Yeah.
piling up.
No, that's fine.
You seem in delta function injection.
No, some power injection, but they are piling up in the point of balance between cooling and.
Yeah, so in principle you can inject, of course, electrons at some. Of course, if you have some. Yeah, no. If you just inject them,
That's no problem.
if you inject them at very high energies, then they will radiate everything there, and they will get cooling spectrum. So you get the trouble.
That's fast cooling.
I guess.
Then you get fast cooling. So
Okay.
you cannot just inject a lot.
Yeah, but if you spend more power for heating of this
Yes.
pile, then that's okay.
Then
You inject it sometimes
Boris,
rare, yes.
Then this injection is energetically negligible, and we forget
Yeah.
this for the moment. Okay.
I guess the question is, you inject new energetic electrons, or you just heat
We
existing
reheat
electrons?
them. We will
So
reheat.
you reheat, you put
We
your
reheat.
energy into
Yeah,
electrons.
because-
or in
Yeah, because that's the important thing. If you think I have I can distribute this energy to all the same electrons all the time, right? As you say, just keep them. Or I choose electrons, give them kicks, but then they cool. Then you get cooling spectrum. So this is impossible. So you have to keep all the electrons heated. You cannot choose.
But if you go to the previous slide, there is something about heating. So it's energy independent heating. Yeah.
I mean, here, of course, you can't understand what this is derivative here. Supposed to be. And this is also somewhat derivative. No, I mean, forget about this. Is just diffusion. So this is second order stochastic
equal
acceleration.
energy per unit time.
Okay, so we have two types. In Monte Carlo code, what Boris did, you take all the electrons and you kick every electron with given kick every time. Every
Same
second.
energy.
Same energy, for example. You can do it proportional to the energy. It doesn't change much. In this kinetic code, we just have second order stochastic sort of second order differential term, which you can with some diffusion coefficient there. So it's sort of it tells you that there is some stochastic acceleration. Yeah, in momentum space, and therefore, and this is heating, and in reality you will get the Maxwell.
Again, the first one, you kick every electron.
Yes.
And
Small kicks. Small kicks. And you give them the same amount of energy every time.
But this, the rate at which you kick them is independent of energy, or?
This doesn't matter. I mean, I think what we did, we had both. We had equal amount of energy per each electron every time, or you can give energy proportional to its energy. The result is still the same. So you have to distribute this energy importantly over all of them.
So where do you use the time dependency? I mean,
we will see now where you will get the time dependency.
yeah,
because if you assume
this
that
will
you
get
have
a steady state after a while.
After a while, yes,
Yeah.
of course. But the steady state can be reached only if you have pair annihilation.
Yeah.
Here, because I mean here then we don't have escape anyway of pairs, so they have to annihilate them. So just an advertisement for the code that's Indrik was writing. This is still one zone, but it's used as a particle distribution down with magnetic field. So these are the processes that I included there: Compton scattering, synchrotron, Coulomb collisions, and all this is done exact, sort of exact Compton scattering kernel, and so on. And sometimes if you, I mean, I will show you some equations. And these are time dependent, coupled integral differential equations basically. And they contain integral and differential terms up to second order. They discretized and then you solve them. So this is typical form of those equations. So these are the processes that are included. Basically, if these are equations for the photon number, let's say derivative of what time here have synchrotron, Compton scattering, pair production, escape maybe injection. The same stuff for sort of electrons. And here this is the written, these are equations how they look when you put them on the computer. So because we discretize the number of particles per logarithmic grid of energies, so you write this is second order differential term. This is sort of cooling or heating, depending on what you have. This is diffusion. And then this could be integral term, which is Compton scattering kernel, for example. And this integral can for electrons and for photons. Then you can also escape and some injection, which could be, for example, annihilation or so on. And so you just solve those questions. And in Monte Carlo code, you don't solve any equation, you just simulate, right? Okay. So 3 examples of those simulations. We didn't put any for the spheric emission, which Asaf already told you what will happen if you put the spheric emission. But here, just example. So these are pure synchrotrons of Compton models, basically. The photons that you get. Pair annihilation is not really interesting here. So there are just synchrotron and Compton. You assume that you have very small optical depth in gas, 10 to minus 8. Compactness is 0.3, so basically you think that you are far away from the central engine. Magnetic field is 10 Gauss here, which corresponds to some comparable compactness in magnetic field. And as I already told you, the typical Lorentz factor of the electron will be 10 to the plus 4. Okay? Just because this is 1 over square root of this tau. And this is what you get in the beginning. This is synchrotron. There is some mass, there is a little bit of Compton. Because already these synchrotron photons are in Kleinian. So there is no Compton for those parameters. What happens later, this is evolution in time, you start producing pairs. And when you start producing pairs, this optical depth grows as it goes here. So therefore the typical Lorentz factor has to drop. Because you have we fix the energy dissipation per volume. Right? So therefore, how much energy gets into the per particle, of course, will drop. Therefore, gamma will decrease, synchrotron peak will shift to the left, and then at some point you can produce quantum. Does it look like gamma reverse? This is sort of that range, for example. Of course, you have synchrotron. The difference is that there is no cooling spectrum here. This is because you keep the electrons heated all the time. So this is optically seeing synchrotron from basically Maxwellian electrons. And this spectrum is of the order of F nu goes like into power 1/3.
So there is something I missed. You talk about a photon compactness there. L equals 0.3.
Yes. This is energy. Total energy.
So this
Energy
is the energy
space.
that you put originally in electrons.
Yes.
All right.
Yes.
So it comes out to.
Yes. So it's of the order of the, of course, photon compactness on
Yeah,
there.
yeah.
So how much energy?
So you cannot set this number as photon compactness at the beginning.
No.
You set it. Okay.
We put this
Yeah,
energy.
yeah.
to
So
the
this is
electron.
according to your initial condition.
Yeah, so this L is not photon radiation. I mean that
Yeah,
of course it is, but it's the energy that you give to the electron. Okay, so of course this kind of spectra, you can get synchrotron to MEV, no problem, but for that you need to have extremely low optical depth.
So is it like an expansion timescale that you...
Yeah, we just so for example here just one dynamical time scale. So it's, if you put this somewhere, let's say 10 to 16 centimeters, and just evolve for the same like ROC, just basically one light crossing time. So this time is a unit of light crossing time of the blob, let's say. So this is 0.3 and here is about 1. So it's one light crossing time what happens. So it's a strong evolution already. Then we did same kind of simulations, but for slightly larger optical depth, which you can think, okay, maybe I am slightly closer to the central engine, optical depth there is larger, so 10 to minus 4 a few times, so the typical Lorentz factor of the electrons will be of the order of 100. So just for simple, here you can think this is Kamu in size, 10 to minus 13 centimeters. Lorentz factor of the jet was just assumed 10 to 130, so this just, we need to know where to shift our spectrum then. And so what happens here, you have synchrotron, but now it's not in Betz range, but it's an optical or UV. This is V band here. And then you have synchrotrons of Compton, one bond.
And this optical is ruled out.
Yeah, I mean, I'm not saying that they are not applying this to a given burst. I'm saying that this is the model that will come out.
Typical bursts do not show this.
Yeah, I'm talking about the model now, not the data. Okay.
But
So,
not
and
the
here, of
data.
course, you can put closer in, you will get more self-absorption. So this can be reduced by orders of magnitude. So it depends where you put the system. I mean, this is the observed range in UV. In the common frame, it will be orders of magnitude lower. You can here. This is self-absorption here. This is actually really genes, basically, because your particles are more or less Maxwellian, so you'll get the really genes here. Okay, so you have synchrotron self-Compton first bump in that range somewhere here, and then you can have the second bump, and then depending on the parameters where this is inclination or not, this bump can be strong or weak.
So I don't know if it's again. How do you?
I mean, typically optical emission is very low.
You said it is not observed. But how can
there are three components here. You're worried very much about the shape of the spectrum. I'm telling you that I'm much worried about the fact that you have your three components, two of which are not observed. So if you compare one model in which the shape of the spectrum is not so great, in another model in which you have three components, and two of which are not observed, I'll say that this model is much worse than the synchrotron model.
Okay, so I would answer exactly opposite. Because we know that there is prompt emission optical, we know that there is MEV emission, and we know GV emission. So there are four, there is components there.
There are very strong upper limit on prompt emission
In most bursts.
in most bursts. And even in this one that there are, you can show that this does not work. But this is a different story. But for most bursts, there are very strong prompt emission on the fourth burst. And because of the fact that you have very strong emission on the first burst, this peak cannot be here, this peak must be here. If this peak is here, this amplification is huge. If this
And then you can
wait
take
a
the
second.
emission.
If this amplification is huge, then this amplification should be huge.
No,
and
no,
wait
no.
a second. And if after the kleine Schienen should be here.
No?
Yes.
Zvi, what you are doing, you are doing Mickey Mouse model of putting numbers in.
But this
What we are doing, we do exact calculation of radiation processes. So these are two different things.
Even the model that you show here on the blackboard is ruled out. Your model.
I am
you
talking
show-
about the
not my
model.
Mickey Mouse model. Your calculation that you show here on the blackboard are ruled out even by Egret observation. You don't have to go to Fermi. Fermi definitely tells you that you don't.
See,
have the
I'm now
same-
talking about the physics. And now, after I'm
I'm
finished with
talking
that,
about-
we can talk about observations, because we see GeV emission
Well,
and we
you
see
begin-
optical
you
emission.
You begin with the fact that there is observational problem, and because of this you rule out one model, and then you go to a second model. And this model, I agree with you that this is what you get. I completely agree that this is what you get. I'm just saying that this model is even more irrelevant.
No,
than observation.
it's not,
Let's
because
just try to
there are,
follow. Okay, what
we
is
don't
not-
know where it's produced, what is the compactness, how strong is self-absorption.
what
There are
is
so
not-
many
There
parameters
are
that
so
we
many
actually
that-
don't know.
If you begin to play with parameters, I can play with
See,
parameters of other models.
You cannot play with injection, because the electrons are injected, they cool. You cannot play with that. Here, there are plenty of parameters which you can play with.
Okay.
So,
So the only thing you
Can
can
I ask
say
what
is
the
that
problem-
these
what is not-
parameters,
what is not
these
observed?
parameters doesn't work.
optical emission, typically is
How
V.
do you-
Optical emission is not
How
observed.
do you know? It's a prompt emission, right?
Prompt
The prompt, the
You're
limits,
talking about
they are
prompt
limited
emission.
of at least 12 magnitude on most birds
But-
on the prompt
The
emission.
question if, you know, if the...
There are limits, I mean, what do you mean?
No, but within, I mean, what is the...
Prompt, simultaneous with the gamma rays. And there are limits from
How can
Fermi
you-
and from Egret on the on the GeV mission. You're not free with these two
No, wait,
components.
what do you mean simultaneous? How can anyone observe the optical emission simultaneous with...
I mean, there are a couple of birds where
There
you
are many-
do
there
observe.
are several
You have to
dozen bears in which optical telescope were pointing during the prompt emission.
Okay, Tzvi, have you ever thought that you can have dust absorption in the galaxy?
In all galaxies.
Or in the wind of the star?
No,
If
you,
these are
you
massive
know,
explosions
you
stars.
know the dust you know the dust limit because you see the afterglow, and from the afterglow you know what's there.
Do we know the model for the afterglow? We haven't discussed it.
No, we don't care about the model for the afterglow. You see the afterglow. From the afterglow, you have limits on the dust emission. So you know that
You can have dust in the winds,
so
because
you know-
prompt emission
no,
inside
so
the wind.
You know that you can see the.
So you see, my feeling is that cooling model, or this fast injection, is completely ruled out. There is no way around it. This model, you can have, if you don't like our optical emissions, you can absorb it, because you can organize stronger absorption. This can be in plain machine, so you can...
If you absorb it, you will not have seed for the second emission.
What do you mean you don't have seed?
Hmm?
What do you mean you don't have seed?
If you absorb it,
Yeah, you need all
You reduce
optical. You will get it in
you
UV.
reduce it. But if you reduce it, you will not have seed for the second.
The energy
component.
will come out, right? The problem is that if you put energy in the electrons, it will have to come out somewhere.
Yes.
And if
will
it
all-
cannot-
and
if it
will all
cannot come out in
it
the
will all come
synchrotron.
out in the GeV.
If it cannot come out in optical, by synchrotron, it will come out by Compton.
And
Whatever
then
you put synchrotron here, of course,
You
what I
also
what I
listen
said
to the
here,
doctor.
Tzvi,
Okay.
that this is pure synchrotron self-Compton model. I mean, if this model will not fit the data, at least this is physical model, okay? And then we can put photospheric emission, maybe it will fit better data, because then you can have MEV emission, for example, prompt from photosphere, and then this optical and GeV might be produced later. But this is another story. I'm saying that this is a physical model, one can compute things here, one can compute this self-consistently, one can get the spectrum out, and then one can compare this to the data. And what I also want to say, that I think what should be done in this business of gamma reverse, one should not try to say, I have synchrotron there, put the power law electrons, and forget about what happens to them. At least one should compute things. There are codes around in the market, as Asaf has, we have the code, and there are other codes like Belmont and Malsak, which have most of the radiation processes that are important, that can compute all the spectra. Therefore, one should use those codes and compare the simulations to the data, and not just making hand-wave arguments that this doesn't fit, this goes there, it's too strong, too weak. Because there are much more serious problems with those injections that people have used for 20 years. From I don't know from what year when recently Sarah wrote this paper. But I mean that's completely wrong. Yes.
Just one thing. There are. I don't know how can we play with the early optical data because I have in my mind some Rotsy, for example, observation for some bursts in like 10 seconds, 20 seconds during
Yes.
the prompt emission. And if you see the light curve of these, usually are R-band or something like that, they are quite well connected with later time. So I don't think you can pair it up with the absorption in the sphere period, because if there is something different,
You
with
can you
respect
have
to the-
absorption inside the source.
No, I agree, but
I think
but if you have absorption at the beginning with these very early times optical observation, and you don't have at later time when you can evaluate the absorption, you must see something in the middle that shows that there is some changing. Sometimes the light curves from these very early times to the later times are very smoothly connected in the optical. So I don't want to enter in the details of the model, but
This is what, I mean, how fast can you slow?
the earliest optical observation we have in sunburst are during the prompt emission in 20 seconds.
1 second after the explosion. And what was-
After the trigger.
After the
Let
trigger.
me use
Chairman
this
starts
parameter.
it up, so we have a problem here in the audience.
That, you know, that's a risky. So you miss
That
most of the.
There are
most
some
of
cases
the
where there is
events.
a small precursor which triggers the observation, and then if there is a long burst, you are there for the main burst. I mean,
We have a
it
couple-
was typically the case for 99 or 123. I mean, there is a small precursor, the robotic telescope.
Okay, so what was roughly the overlap? In percentage of the burst duration, what was the overlap roughly?
No, of course it's a small number of bursts, but there are really a small number of bursts where you have a limit on the optical, a real limit during the prompt.
So we have also optical observation in a couple of cases. I don't remember the names, but I can tell you later. In which the gamma ray instrument trigger on a precursor. Then we have optical observation in between the precursor and the beginning of the prompt phase. So we have this situation, and you actually see the optical, usually B or R band. You have observation, not limit, during this exactly the prompt phase. You have this small peak, you trigger here, you start to observe with the optical in the middle or in the beginning of the prompt phase, and you follow it. And you don't, the light curve, if you connect this first early part with the later one, you don't see anything really particular in many cases. So if there is a lot of absorption here and not after, when you produce the so-called afterglow emission, I would imagine some jump somewhere if there is a big difference in the absorption.
Okay, so we will discuss this.
If this is after you are, there is
Yeah,
limited
okay.
absorption.
I have 3 slides to show, and then after that we have one whole hour for discussion.
Yeah, I think you know it's kind of a wrong conception of this discussion, because you know these numerical calculations are really strong tools. And of course, eventually you have to be compatible with the data, and so the only thing that such a plot says, you take this plot and you compare it with the data, and if it doesn't fit, you just say, okay, this region in parameter space
It's
is
excluded.
rule out.
Exactly.
That's it. I mean, there's no, it's just much better calculation than to do it analytically or to do it, definitely, if some calculation is wrong.
The problem is not the calculation. The problem is the assumption you put into your model. For example, this is one zone, blah blah blah.
No, that's, I mean, we can discuss this. I mean, I think that what I would like to, at least this way of doing things, I mean, I'm not advertising, of course, that this way, but what we are doing. But this is, I think, the only proper way of doing things. I mean, I wrote immediately that this is one zone code. We can, with Boris, we can do with Monte Carlo maybe even multi-zone code, but then it will have more parameters in the problem. If you try to do with single zone code, or we can compute the wind even, that's possible. Nowadays, that's become impossible. You can compute self-consistently all the radiation processes. And then what you will get, and then that you say, what is my physics of particle injection, acceleration, dissipation? What are my parameters? Where I am working? What is the magnetic field size, energy dissipation, and so on? You fix those, you compute the spectrum, and then as a subset, you compare to the data. Does it fit? Does it not fit? My feeling is that gamma ray bursts are very different. As we all know, you've seen one gamma ray burst, yes, you've seen one gamma ray burst. As Kim Page said about afterglows. But sometimes, as Sri said, there is no optical emission with very high, sort of very low upper limit. Sometimes this optical emission is extremely strong. So, do we understand why this was happening? I don't really.
Yuri, but probably think,
That's a question.
there's no one case
I
when
must
they are
have-
the same energetics. I guess the strongest optical emission is like order of 1.5 order of smaller still. But this is an optics.
Okay, let's. I have 3 slides and then we can discuss. So just here, this is another calculation. The same, exactly the same parameters with the inverse code. Similar thing, completely different code. You still see this evolution. That, for example, you can have this emission will be dropping slightly synchrotron, MEV emission will go on up, and then depending on the parameters, you can have GV emission very weak or strong. For example, here you can have very soft emission in GV range. And actually, this is the electron distribution, which looks almost clearly as Maxwellian. Sometimes you have because of pair production. So at least here we can compute things. Okay. Yes.
So before it was Monte Carlo?
Yes. 2 different codes, Monte Carlo and kinetic equations. Same thing. Okay. Final thing for those simulations that we did. Now you assume that the optical depth is unity. So your Lorentz factor is just about unity. So basically it becomes quasi-thermal compensation. Here, remember again, this is pure SSC. So your photons are only synchrotron. Therefore, synchrotron here on the plot here is somewhere here, buried. And now we have multiple complex scattering getting somewhere to 50 keV in the comoving frame. You can put your arbitrary Lorentz factor. Maybe 30 keV, it depends how much, what's the compactness. It could be larger than it could be slightly cooler, the spectrum. The spectrum actually is not very hot. So in these simulations, you will get synchrotron emission, I don't know, 4 as a magnitude below the MEV. And I don't think this will contradict anything what Svi was saying. Just. So, I mean, this is what Asaf said, that look at it, we take parameters and we will remove, or we will, what do you say? We will say that this parameter regime works or doesn't work, we can say, right? To explain the data. Here, you will get very weak optical emission just because electrons are extremely cold. Synchron is extremely self-absorbed here. Nothing will be emitted. And you will have nice power sticking up to. And of course, you have everything in between all those cases. So I'm not sure that we can just ignore this. Okay, so this is just basically thermal compensation. If you put additional soft photons, like for example black body, which are somewhere here, of course this picture will change because you have additional cooling agent. And then we will have to compute this. Summary. Okay. Before we go to discussions, I think we already have a good start for that.
Sounds even.
Synchron and Compton, both of them, of cooling electrons, are strongly contradict the data they produce in 2 soft spectra. And my question is for the last 10 years, how long we are going to ignore this fact? At least one should be aware of that. Cooling can be avoided if you have heating of the dynamical time scale, not instantaneous. Then we can put all this synchrotron or synchrotrons of Compton, quasi-thermal compensation maybe. We can talk about stratospheric emission, might solve the problem of hot spectra. Okay, so then of course if you put stratospheric emission, we don't know what's the radiation mechanism, because then you get much less constraints on from your spectrum. But then we also have optical emission, and the question, one can ask yourself a question, where it's coming from. At some gamma bursts you have strong optical emission. Is it coming simultaneously with gamma rays from the same region? This looks like slightly delayed. So it could be synchrotron somewhere else from larger distances. Reverse shocks, I'm not sure. GV emission, you do see it. There was 94, 10, 17, which was clearly a strong component, and 3 weeks ago it was also a strong component. Seems to it has to come from somewhere.
Not coinciding in time with the low energy emission.
I mean, last burst was 1 second long, so I don't think you can.
There is one case in
Yeah,
which
I
there
mean,
is a strong GeV emission. On a typical, I can show you one burst in which the slope of the low energy component is very soft. So
Yeah. So
does it,
what
does
I'm
it,
saying
does
that
it prove the synchrotron
it doesn't
model?
prove anything. I mean, it just tells you that sometimes it is there, sometimes it's not. And what is the NGV range? One can ask yourself a question. Is it inverse Compton scattering of MEV photons that you see, or is it completely different region? Just a tail of MEV photons. So you can think that you have a tail, and then you have this power distribution that goes sort of to GeV. Then you would have one component. is it prompt or early afterglow, your GeV emission? And so this is the question that I wanted to raise just, what is the energy dissipation, how you heat the electrons? This is what Amir was asking, yeah? What is the physics of it? Because, I mean, could you heat electrons in shocks, not just eject them? Could you heat them? What magnetic reconnection can do? Can they heat electrons? Maybe there are some neutron decays, you just have some also energy dissipation between the neutron flow and proton flow. What are the radiation processes? Synchrotron, Compton large optical depth, quasi-thermal optimization, SSC at low optical depth, what's the role of photosphere? Do you believe that this is explain your hot spectrum? And then of course the important question is how many spectral components do we want in prompt gamma reversed emission? Is it one MEV and the rest is produced at the same time, or these completely unrelated components? What you see in GeV and optical. Yeah. Okay, I'm finished. So now we can.
Do you try to fit something?
No, we don't. Not yet. We just had the code, and I think since gamma bursts are so different, every gamma burst is different. I think it's.
No, just one.
Yeah, I mean, we need to take one. I mean, for one perfect, what you would like to have prompt optical, prompt GeV emission, and MEV at the same time. We don't have a single one.
I think that anybody can find a burst
You know?
which confirms any model.
Yeah, yeah. I mean, if the number of models is smaller than
Like in September. Then or 8 or 9.
There is no optical there.
I think that the situation has changed in the last year and was clarified with Fermi. Because up to now, you could have had doubts, where is the energy? And in the old days, you put a new detector with a different energy band, and suddenly all the photons were in the new band of this detector. And the spectrum was shifting with time because of the response functions of the equipment. Now, I think that Fermi confirmed basically indications that were already before. And I'm talking about a typical burst, not about a special burst, 1 in 100 or 1 in 1% of the burst. Because on a single burst, everything can happen. But we know now that on a typical burst, the high energy and component is not significant. There is no inverse Compton bump like the one which is seen clearly in AGN. If there was such a bump, then Fermi would have been detecting one burst a week, or one burst, which this was some of the earlier predictions, and these papers are on the web, you can find them. This was the earlier prediction. Unfortunately, it would have been great if it was there. It is not there. This was expected because, as I said, Nakar and Sari and Endo have shown that IGRE data already ruled out a very strong inverse component GeV component.
There were
It
some
may
noticeable outliers.
Excuse me?
There are some noticeable outliers to this rule.
Outliers, we don't talk about outliers. Outliers with GRBs, you can find an outlier which will be exception for everything. You spoke at length about the problem with the low energy spectrum. There are some bursts with soft low energy spectrum. So what does it mean? It's not a typical thing. We have to talk about what an average burst is doing. And similarly, it is likely there is no low energy component. So we have to take in no optical component. So this is really the essence of what I was saying and what I was said in my earlier talk. Now you can do a very sophisticated numerical calculations, and of course, the more sophisticated you are, the more details you have to put in the model, and the more details, and the more detailed is the result. But as a basic feature, there is a Y parameter which multiplies the low energy emission to the middle band, and then from the middle band to the high energy band. And Since you have a limit on the low energy band, this Y parameter, if it is there, should be large. And the same Y parameter with Klein-Shihn correction will give you to the high energy component. Since you have limits on both sides, you cannot have, it's very difficult to put inverse Compton source for this. This is all that this is the essence of what I was saying. And,
Okay, so this is written here. Optical emission typically is lower than MEV, and GV emission is typically lower than MEV.
Something very naive. And when I was a first year student, one of the most influential talks that I heard was by an unknown physicist called Taylor, who told us, the audience, that in physics all series converge, including those that you mathematically explicitly prove that they don't converge. And my lesson from this, later as many years of doing numerical calculations, that numerical calculation quite often converge even, and you will agree with me, you get the basic feeling of the result even when the resolution is not so great, and then later you increase the resolution, you do much finer calculation, and you show, and you see that the basic result that you got, which on almost wrong calculation, is not so wrong.
Yes, true, but then you have to do exact.
Wait a second, you spoke for at length, and therefore, it makes sense to get the feeling of what is going on. And the feeling for what is going on is the fact that FMEV is equal to some Y times F optical, and it is equal to some Y prime, and then F GV is equal to some Y tilde times FMEV. And these two Y's are related. And since this is, if this is satisfied, you have these limits and you have to live with them. That's all.
Well, and how you explain dark bursts, how you explain XNFs, how you explain some other things?
We don't explain anything yet. We have
Exactly.
just.
I don't
we just
explain, I'm just showing the problem. I'm
I'm
just showing the problem.
Yeah. Okay, so Tzvi said basically that most of the bursts have most of the emission in MEV range.
Yeah.
And I think, do we agree all with that?
Finally, we know
What the observers will
Finally,
say.
we know this.
No, most of the bursts is it. Okay, Felix, who is doing gamma reverse spectrophy, tells that that's the case. Okay,
Yuri, I agree that that's really a problem. But
well, it's a problem, it's the fact, yeah.
This program can be applied to any optical thin model. This is my feeling. And this is probably, so it's the less severe for this particular model, because you can, for example, suppress synchrotron component by self-absorption. Then you don't need these Y relations. Once you suppress
No, I mean, you have to comptonize something. So basically, you can get them. Three basically said that then Y is life. I mean, you put photospheric emission, then you don't care about it.
But there is still a problem, I agree. But the only solution is just to give up any optical thin model.
Fine. So basically, what we are saying that it seems that we even probably will agree on something that if most of the gamma bursts have really MEV emission terribly dominating all the rest, then the emission cannot be optically thin. Because the moment you have optically thin emission terribly, you will produce synchrotron, you will produce GeV, it will escape. You will see this.
No MEV.
What?
It will not have MEV.
Well, you will see MEV too, there is no problem with that, but you will have also strong components there. So basically what it tells you, for most of the burst, this is optically thick emission.
But what's wrong with continuous acceleration and
It has to be there.
No, what's wrong with continuous acceleration?
And
Optically thin model.
optically thin?
Synchrotron with continuous acceleration.
I showed you what's the
Yeah,
problem.
that's-
You get two
it's
soft
terrible,
spectra,
yeah.
the one,
No,
and then you
with
have...
continuous acceleration. With the electrons.
Yeah, it's the problem is that you get two soft spectra still.
No,
There is
you can find
25% of the gamma burst contradict.
Yeah, and you have a problem of
Wait a second, I was 25% of the gamma burst contradict synchrotron optically thin spectrum. That's one problem. And another problem is that in order to get synchrotron to MEV range in this model, constantly keeping, your optical depth, typical optical depth, has to be 10 to minus 8. So you have nothing to emit. You have no particles. And the question is where you get such optical depth. What is the physical region in the jet with optical depth 10 to minus 8? Because in order to get to MEV range, you have to have huge Lorentz factor of the electrons.
Yes. Yes, you have lower factor of few hundred, or few thousand.
2,000, yeah. So, but I mean, then you have optical depth, because
Random Lorentz factor, yeah?
yes, random Lorentz factor. Lorentz factor of the electrons is optical depth into minus 1/2, as I showed you
So
in this model.
Yes, I agree with you.
So this is a few thousand. The optical depth is 10 to minus 8, or 10 to that.
Yes. But one can arrange parameters to be zero.
No, maybe fine. You can do it. So if you are happy that the emission region contains 10 to minus 8 electrons with optical depth 10 to minus 8, fine. But I mean, if you think that you have a photosphere, I don't know, a typical gamma reverse.
Frederick is doing it all the time.
Who?
Frederick is doing it all the time.
Yeah, but the magnetic, you have magnetic jet.
Yes, fine. So I'm saying that we have synchronous emission. I mean, still, this will be contradicting 25% of the data. 25%.
I mean, to me, the fact that most of them don't show GeV could be just simply explained by, or maybe indication that the Lorentz factor, bulk Lorentz factor of the emission region is not high enough.
That's good, but then you will have a
Sergey told us that a week ago.
Then you will be
I mean, just from the opacity argument, to get less
then you would see you should see the cutoff, and the cutoff is not seen. For example,
cutoff where?
You mean that it's self-absorbed?
No, not self-absorbed.
So what do you mean?
You mean by per production opacity?
This is self-absorbed. This is what I mean self-absorbed.
Yeah, self-absorbed is normally
but
about low energy.
Then you would see since you have now GBM and LAT, you should see probably even in the GBM this cutoff for a high redshift burst, and you don't see.
Why we should have cutoff?
You should see the cutoff. If it is self-absorbed, there is a typical.
It depends on what you say about the source. If you have just pair production inside the source, you don't have any cutoff in the spectrum.
It depends on.
It's a Paolo.
It's a Paolo, but it should.
No, it doesn't.
Why not?
It's a Paolo because you have internal absorption.
Okay, I understand your point. If it's a one-zone model, yes, but if it's
we are all talking about one-zone model.
We are talking about
begin to take.
No, I mean there is
no difference. Only you can do everything.
But I mean, if you have, I can produce a Paolo just by if I have an inhomogeneous source and I take the injection rate to be a Paolo in radius, for example, just for sake of argument, okay? And you inject at any given radius, you inject particles to energies above the pair production, local pair production rate. Then you get the Paolo. I cannot even show you what's the Paolo. So I'm saying. If you want to actually be more careful, if you have an homogeneous model and you have per production, then you can vary the local conditions with radius such that there will be no. I mean, you will still get something like.
If you begin to play with this game, I can give you a distribution of bulk Lorentz factors. If I give you a region in which the emitting region is a distribution of bulk Lorentz factors, this distribution of bulk Lorentz factor will dominate the spectrum. It will change this low energy spectrum as well, just like this.
It's good.
This may be the solution. You get fast cooling, single injection, and just play with the bulk Lorentz factor, because the bulk Lorentz factor give you
I mean, all these games, by the way, all these games were played in the last 5 years in the Blazor community.
It doesn't matter if you make a multiple zone. Fast cooling will be still there.
Now, that's why there was a point at the beginning that I personally don't believe in all this. I mean, it's very convenient for calculation to invoke one-zone models, and it's good because we can all make a living. So that's more important than science. But I mean, if you want to be serious, anytime you look at the source with good resolution, you see it's inhomogeneous. I mean, things are much more complicated. So I mean, realistically, what you're saying may be true. Yeah, the conditional change, along the source, the bulk Lorentz factor may vary. There may be even a transverse.
In this case, I'm asking, what's the point of making this such a sophisticated code?
That's another question.
I'm not sure you can even defend it, though. When you have very spiky emission regions, they have to be single zone models, or at least the single zone has to dominate that emission region.
Yeah.
Otherwise, you get overlapping of multiple emission regions.